Welcome back again. Today, I'm going to talk about time in physics, physical time. In the abstract, had given some rough indication of what I'm going to talk about. It was to highlight the inseparable link between gravity and the modification of time, and take a close look at the precision operation of GPS-like systems, which everybody is familiar with. And the idea was to show that what you see is not what you think it is. There is a algorithm which runs behind the GPS-like system in which relativity is used for the corrections on time of the atomic clocks used in those systems. And I wanted to talk about that. Then I wanted to examine Einstein's exposition of the relativity of simultaneity. That is, how do you decide whether two events are happening at the same time? So, wanted to analyze, look at his analysis, then follow its consequences. The focus of this lecture is physical time and its modification by gravity and motion. The reason I'm discussing this in this series of gravitational wave talks, GW at Home series, are many. Both light and gravitational waves reach us from very far, even billions of years of distance, light years of distance. They link space and time in current physics. They bring together the past there to the present here. Then precision timing in astrophysical signals, precision timing of astrophysical signals are very important in gravitational wave detection for source position identification and even for the operation of the detector itself, which already in some talks people have mentioned. We are dependent on the precision of keeping time for navigation, location identification, commerce, etc. So, without even our knowing, we are dependent on nanosecond level precision of global time. So, using global navigation satellite systems, what are called GNSS systems, examples are GPS, Galileo, GLONASS, and so on. So maintaining a common time accurate to a nanosecond have become important even in daily life. I do not want to discuss in detail the notion of time and its peculiarities as a concept in physics. I could perhaps on another occasion, because I just completed writing a book on time and gravity after extensive studies on physical time. The book is called Gravity's Time, but that is for another occasion. But today, we focus on how and why time is modified by gravity and motion. How is time related to the propagation of gravitational waves and light? And also the subtle and important physics involved in the seemingly simple task of synchronizing two clocks at two places. How do you make sure that times at two different places are the same? Then you will see that we are already in the deep canyon of fundamental physics, discovering new insight that should lead to a revision of the physics we believe in. Now let's look at two instances where the precision timing is important in gravitational wave detection and gravitational wave astronomy. We are already familiar with the detection of the first gravitational wave signal. And here we can see signals from the Hanford detector and the Livingston detector. These are two gravitational wave LIGO detectors, which are apart by 3,000 kilometers. And they have a slight delay, only a few milliseconds. In fact, the coincident detection that the same signal is detected in both detectors is very important in confirming that it's a astrophysical signal, as you know. So when the distance is about 3,000 kilometers, one would have a maximum delay that can be there is just 10 milliseconds. All the signals should be within that coincidence time. But it's a millisecond level timing accuracy to be kept by the detectors. And this is easy timing. That is not a difficult task. But it is important. In the same detection, there is another aspect which is involved, which is to find the position of the source. This is since gravitational wave detectors are not telescopes. By each of them, they are just receivers of gravitational wave strain from any direction with some selectivity in their sensitivity. But one need more than one detector to find out the source direction. That is done by, if there are two detectors, for example, with a baseline D, if the wave is coming directly from zenith, of course, there is no time delay when it reaches the two detectors. But if it's coming from some other direction, there's a time delay. And this delta t, the time difference, multiplied by the velocity of the wave, c, will give you this inclination. And when there are three detectors, you can find two angles on the sky, and that's how position is measured. Now, 1 microsecond of error is equivalent to 300 meters multiplying by the velocity of the waves. So, for detectors separated by 3,000 kilometers, this corresponds to error in angle of only 0.01 degree. Okay, that is not a very large error because the angular size of even a single galaxy, 300 million light years, is larger than this 0.01 degree. So this precision is more than enough for source direction finding. However, the clocks at these two distant detectors have to be synchronized with this accuracy, for which signals have to go from between these two stations over thousands of kilometers. So we are talking about synchronizing the clocks at two different places. How do we synchronize two clocks separated by a distance? One way is to send a signal. And of course, a signal of choice is electromagnetic waves. It can be microwave signals, radio signals, or visible light. Any of those signals can be sent from one clock to another to do synchronization. But we should remember that we are on the moving and rotating Earth. So how do we make sure that the time at these two places are the same? Because we need this, we are not sure whether the delta t of one trip is the same as delta t of the return trip of the signal. Therefore, synchronizing two clocks depends on our assumptions of the propagation of the signals. It is very, very important. So the questions arise at this stage are, what is the speed to be assumed for the propagation of the signal? What are the factors affecting this propagation? Can we send it in an optical fiber? What is the relative velocity of light in an optical fiber in a moving frame? That is not an easy question. How do we verify that the clocks are indeed synchronized? Suppose we have some assumptions on this, synchronize the signals, synchronize the clocks, and how do we verify the synchronization? Then there is another way of synchronizing two clocks without sending a signal. You synchronize a clock with another clock which is transportable. And then you can transport that clock to the other location. It is not easy, but it can be done. And the other clock can be synchronized. Then the clocks should be synchronized by assumption. Again, since we are on a moving and rotating Earth, several questions arise. What happens to time in a clock that is moving? There needs to be a theory. It has to be supported by experiments. What speed should I use for the calculation of the changes in the rate of the clock? Is it the velocity of the transport, Or should I add the velocity of the Earth, velocity of rotation? It's a difficult question. It is a very conceptually very deep question. How do we verify that the clocks are indeed synchronized again? In fact, the only verifiable synchronization that is independent of any theory is when the synchronization is done at the same spatial points, when the clocks are at the same place. In fact, for thousands and millions of years, the only clock which was really available, precision clock, was the rotating Earth. And our 1 second was defined as 1 divided by 86,400 of the mean solar day. Standing on the Earth, we see everything, including the sun, going around periodically once a day, which takes 86,400 seconds. And so that is how the second is defined. This is an incredible clock. Its stability is it is stable at 1 millisecond in 100 years. So the mean rotation rate of the Earth doesn't change very much because of its massive body. So this corresponds to 10 to the minus 12 as the stability of this clock. What it means is you had to wait for about 100 years to see a difference in the rotation rate amounting to a millisecond. Now, only in about the mid 20th century, we changed from this terrestrial clock to atomic clocks. And the atomic clocks are, of course, better than this clock, Earth clock, in terms of the stability. Their stability can range from 10 to the minus 13 to 10 minus 17, which is an incredible achievement of atomic clock makers. Already there was a talk on these issues. So what are the atomic clocks in use today? What are their precision and stability? They are at this level. Now the question is, how are atomic clocks synchronized across the globe and satellites, amounting to this kind of a precision that is less than a picosecond or nanosecond, and so on. So we are talking about synchronizing two clocks which are separated by 20 to 30,000 kilometers, but the claim is that they keep the same time within a picosecond or so. How is it done? Now, every clock needs an oscillator or a periodic physical process. The atom has neither. The de Broglie wave and so on of quantum mechanics is unobservable abstract entity. This is not a real oscillator which we have access to. An electromagnetic wave can move electrons, and that current can be detected. So in an electromagnetic wave, its oscillation can be directly seen, provided the frequency of these waves is not very high. So it's practically in microwave frequencies, but the periodicity on optical signal is much shorter. It's 10 to the 14, 15 hertz, and that cannot be detected directly yet. In fact, one can look at this book, Splitting the Second, the story of atomic time, for a history of all this, because this is not the topic I want to discuss. Now, as I said, every clock needs an oscillator with a stable periodicity like a pendulum. And there is a set of gears which are required to bring the oscillation frequency down to a second if the oscillation frequency is very high. For example, if you have a quartz clock, its oscillator is a quartz crystal, which is cut very precisely so that it has some natural oscillation frequency, and that's the oscillator of the clock. It's a very high frequency. It can be several kilohertz, several tens of kilohertz, and then it has to be brought down to a second by a set of gears, and in this case, it's an electronic gear, electronic divider of the oscillations. In the case of an atomic clock, what is done is each atom has transition levels for example, cesium has a transition at 852 nanometers. It also has a ground state which is split into two, in which the electrons are normally in the lower ground state. And there's a difference of 9.2 gigahertz multiplied by H energy difference between the ground states of cesium. Now, when the electrons are here, and if you try to excite it from the upper level to the next high level using the laser, nothing will happen. Laser will just pass through, and the transmission is some value here. Now, if you apply this microwave at this frequency, then the electrons can make a transition from the lower ground state to the upper ground state. When that happens, the atom will start absorbing light very strongly from the laser. So you get a absorption like this, transmission most of the region, but right at the resonance, it gets absorbed. Now, only if you keep the resonance frequency of the microwave exactly at 9.2 gigahertz, like at the particular value, this absorption from the laser will happen consistently. So that's the idea of a atomic clock. There is no oscillator there really. It's absorption of lasers at a particular frequency, which is controlled by another resonance. It's a double resonance situation. And the microwave frequency is what is adjusted so that this absorption is exactly at that point. You have laser passing through the medium of cesium here. There's a microwave. You get a double resonance, and you get a and so this is just a reference for a frequency, which you have to, when one has to divide down to the second level, and you get a 1 second, 1 pulse per second kind of a signal from the electronics. That's how the atomic clocks work. And they can have various stabilities down to 10 minus 7. The picture of the first cesium frequency reference made by Louis Essen in National Physical Laboratory in UK with his collaborator Perry. They are looking at their setup in 1950s. By the way, Louis Essen is also the scientist who was responsible for the modern atomic definition of the second in terms of the cesium frequency. He also fixed the velocity of light from the cavity measurements of wavelength and frequency. He's a well-known figure in metrology. Now, there are atomic clocks can be low-cost rubidium clocks, which cost just a $1,000 kind of thing. These are actually clocks from our own laboratory, just palm-size atomic clocks made of rubidium. Now, in a global network of more sophisticated atomic clocks define the international atomic time. They are made of also these atoms, but now laser cooled and so on. Now, I want to discuss this process of synchronizing two clocks in some detail. Suppose we have two clocks separated by some distance. How do we synchronize? How do we make sure that they read the same time? One can send a pulse from one clock to another at, say, time 0 of this clock. And that pulse reaches the other clock at some particular time. And this clock can set that instant as its own 0. Of course, at this stage, clocks are not synchronized because it has taken some time for the clock to come here. It has set 0 here, but by then this clock has moved up. So this clock can reflect back the same signal at its 0, and it reaches the other clock. So the total time for the up and down trip, let's say is t. But we still don't know whether these two clocks can be at the same time. For that, we have to assume something about the propagation of the signal. because we don't know this distance very accurate. Because for the kind of accuracies we are talking about in synchronization, there is no point measuring this distance approximately. Now we make the assumption that the signal velocity is constant in both ways. For example, we assume that the velocity of light is constant in both trips, up and down. In that case, we can say that here, if the total time is t, here it must have reached a t by 2, half the time. So what is done is shown in this simple space-time diagram. The pulse starts from here, it travels at velocity c, then it reflects and come back at velocity of c. Total time is t, halfway is t by 2. Then we assume that they are synchronized. But it is subject to the assumption that signal velocity is constant both ways. Both will read t by 2. But, however, if the relative velocity of light is not a constant, then this assumption of synchronization is false. After all, the invariance of the relative velocity of light is just a hypothesis. To highlight this, remember that we could be in a moving frame like the Earth. It is moving through the universe. It is moving around the sun. It has a rotation, orbital velocity, and so on. Now, when the signal goes from here, there, suppose it is not really C, but it's Galilean, C minus V. Suppose that is the case. And when it returns, it will be C plus V. So the up trip has one velocity and the return trip has a different relative velocity for the signal. Therefore, now the situation is like this. We cannot assume that both ways it is C. One way it is C minus V. It takes more time to reach the other clock. Return trip is C plus V. Less time to reach back. Total time is still T. Total time has not changed. But when it reaches the other clock, it is not at T by 2, but at a slightly different time, slightly later. So if this clock is set as 0 here, there will be error. And this error you can calculate, it is LV square by LV by C square. LV by C square. So therefore, the two clocks are not truly synchronized. The distant clock is running ahead by LV by C square. You can see that this particular quantity, LV by C square, in the synchronization is also the same quantity which appears in Lorentz transformation with the opposite sign, which is very, very clear indication that that is a thing you have to do to erase this unsynchronization, the gap in the synchronization, to pretend that things are synchronized. But let me not go into details of that. What I'm saying is, with the Earth's velocity in the orbit around the sun, if you consider that, if you have a synchronization signal between Paris and Delhi, the error could be at least 2.3 microseconds. Remember that 2.3 microseconds is 1,000,000 times larger error than the precision of the clock, the accuracy of the clock, which is at 10 to the minus 12 or 10 to the minus 13 level. So it's a very serious thing, this assumption of propagation. At this point, I wanted to show something from Einstein. He says in one of his writings, the theoretical scientific researcher is not to be envied because nature, or more precisely put, experiment, is a merciless and not very kindly judge of his efforts. She never says yes to a theory. In the best case, merely perhaps. But in most cases, simply no. If an experiment agrees with the theory, it means perhaps. If it does not agree, then it means no. Every theory is sure to experience its no someday. Most theories already do soon after their formulation. So he highlights the importance of experiments and data to decide theories. Now, let's go to the next step. When you look at clocks, any clock, precision or otherwise, there are three very important aspects which are related to the physical time. These are the physical modifications of time possible, and the physical, how exactly the theoretical nature of physics enters in actually operating these clocks globally. And the effects of these are these three things: modification of time due to gravity, modification of time due to motion, and the synchronization of separator clocks. The effects are mostly directly and vividly seen in GNSS system like the GPS. So I will use that as an example. But of course, one could see the same things in laboratory experiments also. But since GPS is accessible to everybody, I thought that's a good example we could take. Now, if you look at GPS, as you know, we use the satellites which are going around the Earth at a great distance, 26,000 to 40,000 kilometers from the center of the Earth. And they are all moving at varying velocities of the order of 8-9 kilometers per second. So there is both gravitational effects on the clock, atomic clocks in the satellites, as well as motional effects. And then they have to be synchronized between Earth and this great distance. So all these aspects come in this GPS kind of a system. Now, you know that a rate of clock can be modified by gravity. If there's a clock near the surface of the Earth, there's a clock at a height h. These two clocks do not run at the same rate. The formula for the rate of clocks in general relativity, gravitational time delay, is given by this, where G00 is part of the metric, which is the coefficient for the time coordinate. Now, it is related to the potential, gravitational potential, Gm by R. And you can see this is a formula. The clock here, its rate depends on the potential here. And for the clock there, the rate depends on the potential here. And there's a difference in these potentials because the radius from the center of the Earth are different, distance from the center of the Earth are different, and we have different rates. So the time difference between these two clocks, which is called the gravitational relative time dilation, is just the difference of these two, which is given by this expression. Depends on the difference in potentials. So if you know the distance, you can calculate this and accurately estimate this, because the potential is Gm by R, which is some small correction for the ellipticity of the Earth and various distortions, density variations, and so on. Now, the height in a GNSS satellite can be 20,000 depending, or to 35,000 kilometers, depending on how the satellite is operated. If it is semi-day, 2 orbits every day, then it's about 20,000 kilometers from the surface. Geostationary almost. Then, like the Indian system, which is not a global navigational system, they use satellites at much higher height. So, depending on this distance, you can calculate this. Anyway, the point is that the satellite the atomic clocks in the satellite run faster than the clocks near the Earth. Here, the clocks near the Earth run slower because the potential is larger. Magnitude of the potential is larger. It amounts to about 0.5 nanoseconds every second, the change, the correction. If gravity is not there, it is some t. Once gravity is considered, it is 0.5 nanosecond difference for every second. That corresponds to about 15 centimeters, not per second, 15 centimeters in terms of the navigational error in distance. Now, I'll also show this other formula. When h is small compared to the radius of the Earth, we can approximate this difference in potential by the gradient of the potential. Then you get a more familiar laboratory formula for the time dilation, but that is not relevant for GPS. Now there's another effect, which is that moving clocks age more slowly. This is motional time dilation from special relativity, which is very familiar, which for everybody, and the textbook describe all this. So if there's a clock which is moved relatively to another clock and is brought back, one can calculate the time dilation. This is given by this formula in special relativity. It is as if you travel some distance, you lose some, you gain some time, the clock goes slower. And this is a formula, therefore, square root of 1 minus v square by c square will come. And the point is, you have a trajectory of movement. You just add this elementary dt for every step of this trajectory. And when you come back, you can add all these contributions and you get a total time dilation. Now, so these are the gravitational time dilation and the motional time dilation. There are only two ways to get time dilation. Now, why do rates of clocks slow down in a gravitational field? We can say a clock is a physical process in some form of matter. Without matter, there is no concept of time. If you remove all matter from space, and if you try to imagine what time is, you will fail for sure. Only when there is matter and a physical process, real physical process, a clock and time is definable. Anyway, that's another matter. It's the rate of this physical process that is modified by gravity. The only way this can happen to all kinds of clocks the same way is through modification of inertia by gravity of matter around. So this is a basic reason for gravitational time dilation. But in terms of formula, it's a universal formula given in terms of metric and so on. So since gravity is an interaction, it is reasonable that a physical process is affected by this interaction. That we understand. But why do the rates of clocks change when they are in relative motion? That's a very difficult question. A clock just moves relatively. There is not even absolute motion. We don't even know whether that clock is really moving. That clock is apparently moving. It could be us moving or that clock moving. The relative motion is exactly the same. Why does such a clock, the rate of a clock, gets affected? Nobody knows the answer for that. There is no interaction to affect physical processes in the clocks in this case. However, we say moving clocks slow down. That is from special relativity, or any theory of relativity has such statements. But a relative velocity is the difference between two velocities of two bodies. They are independent bodies. For example, if you have two clocks, from the point of view of this clock, the other clock is relatively moving. However, the point of view of this clock, the other clock is moving the opposite direction. In the relative motion, you can only say the relative separation is changing. We cannot say which clock is really moving. In fact, there are infinite ways to resolve the one relative velocity between two clocks. Both could be moving as well. Now, how do we decide which clock is going slower? As you know, this was a basic reason why there was controversy like the twin paradox for a long time. Okay. Now I want to show something. I don't want to talk about twin paradox here because it's not appropriate to discuss that in a short time. However, it is universally said in every textbook of special relativity that is there is no paradox. It can be handled completely within special relativity. No gravity is involved, and so on and so forth. Essentially, all textbook will tell you this. All teachers will teach you this. However, I want to show just one counter point to this by none other than the creator of these two theories, general relativity and special theory of relativity, was Einstein. Einstein published a paper in 1918 called, in a prominent journal, called a dialogue about objections to the theory of relativity. This is 1918. No textbook of special relativity refers to this paper. In this paper, he said the twin paradox cannot, it's a paper on twin paradox. It's the only paper he wrote on twin paradox. And in which he says special relativity cannot solve the twin paradox because it's a symmetrical theory. All inertial observers are equal in special relativity, so it cannot be solved. He admitted that the special relativity time dilation is symmetric between the two clocks. Then he said the only way to solve that is by using general theory of relativity, the equivalence principle, and the gravitational field in an accelerated frame. All this needs, and the formula for gravitational time dilation has to be directly used. I'm not going to talk about this paper. There's a reference here in which I had written about this in Current Science. People can look at it. 2005. So Einstein is at variance with all the relativity textbook. So if you say that no, Einstein's argument is not correct and special relativity textbooks are correct on this matter, then you are also dismissing equivalence principle and things like that. Now, there is another curious thing sometimes I like to show, which is to show that two clocks flying backwards run slower. This is a relative motion which is seen from one relative motion seen from one aircraft, the relative motion of another aircraft. But the aircraft is moving backwards. And you can wonder whether a clock in this aircraft will go slow or fast relative to the clock in the rest aircraft here. I'm not going to answer this question. It is just for you to wonder about. But I want to show you one example where there's an experiment which is to be discussed. For example, suppose you have a clock here, two clocks, which are synchronized, say near Mumbai, and I want to take it to West, to Paris, US, and so on. So I move one of these clocks. Now, everybody would say this clock which is moved should be going slower. Of course, we cannot see how the time is going here because it is already far away. But it must be going slower using the special theory of relativity. But it can be moved further. It can be moved further, and finally it can be brought back. Since Earth is a globe, it will come back to Mumbai. Now one can ask the question, is a clock slower or faster relative to the clock which is stationary in my laboratory in Mumbai? Of course, the transporter clock should go slower. But the fact is that this clock, which was taken westwards, when it comes back, you will see that its time has run faster, not slower. There is no time dilation. The time dilation happened to the stationary clock, which is sitting in the laboratory. So these are just instances where your expectation is violated by actual fact. Let's go back to GPS. GPS works by the principle that it sends a signal from the satellite with the timestamp of the clocks atomic clocks in the satellite to Earth. This electromagnetic signal is received on Earth from different satellites. So you have time difference between a clock there and a clock here. That's the only signal in GPS, time differences. Then you use special relativity to multiply the time difference by the constant velocity of light c to get a distance to the satellite at the time of emission of the signal. In principle, when you have three such distances, you can locate yourself in three-dimensional space. But you need one more satellite because though there are atomic clocks in all these satellites which are in the GPS system, your mobile phone doesn't have an atomic clock. It is not a very accurate clock. So the time differences of these three signals, that will not be enough to define precision time. You need a fourth satellite, so that when you have four signals, you can eliminate the inaccurate time of your own mobile phone from the whole consideration, and then you can get precision estimate of all these time differences, and you can use a special relativistic formula and get the exact location. That's a system, GPS system. It's a very simple system, and the time difference is the key, and the assumption of the constant velocity of light. These are the key concepts which go in. As you know, there are various systems. The GPS, there is GLONASS, Russian system, Galileo, European, Indian system, which is a local kind of a system. Then there is China, Japan, and so on. So there are very large number of satellites, hundreds of satellites now. GPS signal is an electromagnetic signal at 1.5 gigahertz. It is transmitted at about 100 watts from the satellite, but when it reaches the Earth, it's only femtowatt per meter square. It's an extremely small signal buried deep in the noise. Typical GSM mobile phone power is in microwatts. This is in femtowatts, 9 orders smaller. Electronic noise in the receiver, in the phone and so on, is 100 times larger. However, we can still pull out this information using what is called matched filter. This is extensively used in the gravity wave data analysis, as you know. But the same technique is what is used in GPS kind of systems, which are also very old system. It's a very old technique, matched filter. The difference is that in gravitational waves, the matched filter is you don't know what the signal is. So you have to search in a very large number of templates. Whereas here we already know what signal is, exactly what the coding of the signal is from the satellite. So it is a much easier task. So the signal comes and there's a time difference. What you do is you shift the signal in the local receiver till there is a match between that signal and what you received here, and the time difference is measured from that shift. Now, the point is, once you match this, you have a location. But since the clocks in the satellites have time dilation due to gravity and the motion, both had to be corrected every now and then. Otherwise, a vehicle will go off the road in a few seconds, few tens of seconds. For example, gravitational time dilation causes an error of 1 meter navigation error in about 6 seconds, and the motional time dilation may be about 10-15 seconds. So satellite clocks this is very easy. For the gravitational time dilation, we know this formula and it has to be applied. You can correct it. For the satellite clocks, the satellite go around the Earth, and with that velocity, you can correct for the motional time dilation as well using the special relativistic formula I gave. However, you see that V here. What is this V? This is a relative velocity. Okay, in special relativity. How do you get this relative velocity? You can look at the satellite velocity, which is determined by the Keplerian formula. Using the Kepler's formula of one object going around in orbit around the another, you can get this velocity. And there is a velocity of the clocks on the Earth, which may be moving because of the rotation of the Earth or because it is in a very fast vehicle and so on. So this is a relative velocity. So the VR, which should be applied, is this difference square is what is required, and this is a formula you will get. So there is satellite velocity, there is a local receiver velocity, and there's a dot product of the two. However, if suppose for some reason special relativity and the assumption of the constant velocity of light are not correct, then suppose there is an absolute frame, like the old either, or it's a new universe. Universe is something which we know exists, so it can be the absolute frame. Then the prediction will be completely different, because then this V here has to be the V of each clock. We have to calculate its time dilation, absolute time dilation, take the difference, and that's a relative time dilation. So then you get a formula here, which is entirely different from this formula. Only the first time is the same. The rest of the terms are different. So you have two formula here. One is special relativity, one is an absolute frame theory, relativity theory. For the synchronization, I already said, what is used is the special relativity formula. However, but suppose that assumption of constant velocity is not right. Suppose it is actual velocity is Galilean, c plus v plus minus v, like sound. Then the formula will be very different, because now the delta t will be distance divided by c, distance divided by c minus v or c plus v and so on. That if you evaluate, you get a different formula. Instead of d by c as delta t, it's just a correction. D dot v divided by c square. Then the range formula is very different. Instead of distance to the satellite c times delta t, it will be c times delta t plus a correction. Okay, so these are the two things. Now, there are corrections applied to the GPS satellite clocks. Let's see what actual corrections are. What is actually done in every GNSS system. But let us see. Of course, the time dilation, gravitational time dilation is accurately taken care of by the formula we saw, with a correction for the quadrupole moment of the Earth and so on. That let's not worry about that. Then the satellite velocity. Then there is a term, which is this, and it's not the term which is used in special relativity. This is a formula which comes from the theory of relativity with absolute frame, like the ether theory. This is what is actually used in GPS, not the other formula. Similarly, there is another correction for the synchronization, which is required in GPS. It came later when people realized it, they included it. They call it the SINAT term. And that term is actually the term what you get if you say that the velocity of light is not a constant, but it's a c minus v or c plus v Galilean. You get exactly that formula. You can see here. So the summary is that there is a gravitational time dilation, there is a motion time dilation, there is synchronization. All this has to be done for a GPS system to work. Einstein's theory of relativity gives the formula for each one of them. These are the formula which we already saw. This is from general theory, this is from special theory. An absolute frame theory, like where the velocity of light is Galilean, c plus minus v, where the velocity is not a constant. It also gives formulae for the same effects. So these are two different theories. What are the formula actually used in GPS, GLONASS, NAVIC, etc.? It is not this. Only the gravitational time dilation is common. These are not used. What is used is this formula. So the actual GNS system, all of them use an absolute frame theory, Galilean velocity of light, and that is an actual situation. Hence, GPS in your light mobile phone is your pocket proof and everyday reminder that you are carrying the burden of a grossly incorrect theory. Anybody can check and verify this. GPS scientists will say Earth is rotating, therefore they don't want to use it as an inertial frame and so on. Anyway, I don't want to go into details. If you look at a fast aeroplane, like very fast airplane near the poles, the rotation of the Earth doesn't participate for some vehicle which is near the pole. Only when it is near the equator, the rotational velocity is important. Even there, you have to apply exactly the same corrections, but I don't want to go into detail of that. So where exactly is the problem? Where exactly is the problem? With this, with discussing, once we find this problem, we end this talk. The problem is in the concept of simultaneity. It's a central concept in the notion of global time and its synchronization. When you have different clocks at various distances, how do we know what the time of these clocks are? There is no way to know unless you bring the time of those clocks to one central location. Only a clock which is in the same location can be synchronized. Only the time of a clock which is locally there, you can know the actual time. So a single clock, single location, it's okay. Simultaneity of signals is well defined. But simultaneity of event depends on the convention when the distances are unknown. You have to assume something about the propagation. Even if the distances are known, simultaneity of event depends on what assumes for the relative velocity of light. This whole system could be in a moving frame, like the solar system moving through the universe. So but this concept is very important because it's the basis of relativity, Lorentz transformations, relativistic metrology, GPS clocks and synchronization, etc. I quote from Max Planck, 1909. The gist of principle of relativity is the following. It's in no way possible to detect the motion of a body relative to empty space. In fact, there is absolutely no physical sense in speaking about such motion. If therefore two observers move with uniform but different velocities, then each of the two with the same right may assert that with respect to empty space, he is at rest. And there is no physical method of measurement enabling us to decide in favor of one or the other. All observers in inertial motion are equal. If you take two observers in two reference frames, O and O prime, suppose two events happen at these 2 points. So these observers are at the midpoint. They are equidistant from the two ends in both vehicles. And there are two events which are happening. And we want to decide whether these two events are simultaneous or not. Of course, sitting here, we cannot decide that unless some signal comes from these two events to this position. Now, from the point of view of the frame O, the other frame is moving at some velocity like this. And the events, signal from the event come here. Let's say simultaneously it comes. So for the frame O, it has come simultaneously at velocity, equal velocity c, because we have assumed that the velocity of light is an invariant constant c in every inertial frame. The fact that O prime is moving doesn't concern O. It is in his experience, both these events go off, signals come, and let's say that they come simultaneously. Then he knows that they happen also simultaneously. The fact that both signals are received at the same time, and since he is at the midpoint, he knows that the both events also happened at the same time, simultaneous. Now, what from the frame of O prime? What if we change the O prime frame? Then this is a rest frame. The other frame is moving. But the other frame is moving or not, it's not our concern. In this frame, the experience, the relative velocity is exactly the same. So it's the same experience. There are two events which are happening. The velocity of signal from each of those events is exactly the same, c. So they will reach the observer at exactly the same time. If it happened at exactly the same time for one observer, it will happen for every other inertial observer who was at the midpoint when the event happened. Okay, that's obvious. The relative velocity of light is independent of the velocity of the source and the observer, as special relativity assumes. Two events that are simultaneous to one observer will be simultaneous also to another who is in relative motion, provided the velocity of light is the same invariant constant in both. Both are with equal rights. They have the claim of being at rest, as Max Planck said. But instead, if the velocity of light is Galilean, in one frame it is c, but in another frame it is c plus minus v, then what happens? Of course, in the first frame, let's say it happens simultaneously. But in the other frame, it cannot happen because now the other frame, the velocity is c plus and minus v. So one signal will reach this, since this frame is moving towards a prime, that signal will reach faster, c plus v. This signal will reach slower at c minus v, and they will reach one after the other. There is no simultaneity. If the relative velocity of light is not an invariant constant, two events that are simultaneous to one observer will not be simultaneous to another who is in relative motion. They will be perceived successively, one after the other. This also should be obvious. Which scenario is consistent with experiments and experience? Remember what Einstein said. Finally, experiments should decide. I want to stress it once more by using sound, for example. Suppose you are using sound for signaling. Then two clocks equidistant from you, you are at rest relative to all this. Of course, the sound will reach simultaneously. If their alarms went off simultaneously, it will reach you simultaneously. But look at it from an observer who is moving towards one of the clocks on a bicycle or something. In his rest frame, the velocity of light, velocity of sound is not equal from the front and from his back. From one clock, the velocity of sound is larger. In his rest frame, he is moving towards that. In his rest frame, it is larger. And the other clock, from the other clock, it is smaller. Therefore, the signals will reach at different times. One signal will reach first, the other will reach later. The clocks are moving also, but the movement of the clocks doesn't matter either for sound or light. The movement of the clock doesn't affect the velocity of the waves for either for sound or for light. It's a velocity of observer which is important. So we know that two distant events judged as simultaneous by one observer will be perceived as successive by another when and only when the relative velocity of the messenger waves is Galilean, not constant. So we know the answer here. In one frame, if it is simultaneous, this is one scenario. In all frames, it is simultaneous. Another scenario is, in one frame it is simultaneous, in another frame it is not simultaneous. This happens only when the velocity of light is Galilean, c plus or minus v. Now, we cannot have both an invariant relative velocity of light and simultaneity for one becoming succession for another. These two things cannot go together. If a theory has both these, then the theory is inconsistent. Now, Einstein asked this exactly the same question in a very famous book, which must be familiar to everybody because everybody must have read it. It's called Einstein's book, Relativity, the Special and General Theory. English translation were available in 1920. He asked the following question. Are two events, two strokes of lighting A and B, which are simultaneous with reference to the railway embankment also simultaneous relative to the train. So that the relative motion between a train and a platform is asking the same question. There are two observers at the midpoint, and he's asking if it reaches simultaneously for one observer, what will the other observer will see? We already saw the answer for this. If the velocity of light is assumed to be an invariant constant, then if it is constant for one, if it is simultaneous for one, it has to be simultaneous for the another. It's only when the velocity of light is not a constant. If it is simultaneous for one, it will not be simultaneous for the another. So after asking this question, Einstein does the analysis. You can go back and read this book very, very carefully. In fact, it should be read very, very carefully, because what happened was very surprising. He concluded the following. He concluded exactly the opposite of what he should have. Observers who take the railway train as their reference body must therefore come to the conclusion that lightning flash B took place earlier than the lightning flash A. We thus arrive at the important result. Events which are simultaneous with reference to the embankment are not simultaneous with respect to the train, and vice versa. Relativity of simultaneity. You can see very plainly that he inadvertently used Galilean light to arrive at the conclusion, whereas he assumed an invariant velocity for light and forgot about the assumption while analyzing simultaneity. He did Lorentz transformation, he did all predictions, everything. But when he analyzed simultaneity, he did the analysis incorrectly. You should go back and verify for yourself what I'm saying is right. There's a fatal error in the formulation of special relativity happened that renders the theory inconsistent. It was made by Einstein himself. Anybody can read his writings and verify this, either the 1905 paper or that book in leisure. One can look at these details. In fact, the philosopher Henry Bergson had already pointed out this same thing in his monograph, Duration and Simultaneity. So you see, we know what is happening, why the GPS system has to use formulae which has absolute frame and Galilean light, because that is a fact. That's the only consistent way of doing these things. You cannot use special relativity formula in real systems like GPS. And that's why I said GPS is the pocket proof, which everybody has. Every school, every person in the public, students, scientists, everybody has that in the mobile phones, and it's everyday reminder that you are carrying algorithm, which is not from the current day physics theories, but from the absolute frame theory. All this prove one factor conclusively. There is indeed an absolute frame for motion, and there is absolute universal time. Now, the question is, what is the nature of that time? Can we identify it and consistently build new physics? Most certainly. A master absolute frame is in fact the matter-filled universe. I mentioned it even in the last lecture. It's the gravity of that enormous amount of matter that controls dynamics, velocity of light and gravitational waves, the rate of moving clocks, etc. The absolute universal time is a cosmological time, physically manifest in the temperature of the cosmic microwave background radiation or in the expansion of the universe. It's the same synchronized time everywhere in the universe. And if you want to see some details, you can go back and read it's open access, New Gravitational Paradigm for Relativity and Dynamics, a recent paper which I wrote about all this. So therefore, the factual and reliable markers of absolute time and absolute space is the universe itself, and the cosmic microwave background serves as a practical way of marking time. It allows an accurate measurement of motion, and its temperature is the universal time. the same synchronized time everywhere. Thank you. With this, I stop this lecture here. You can see that you had to go back and re-examine many things you know already. Now I'll take some questions. Shall I answer these questions right now? Anybody there? Questions from Avinash. Let me see. One, can we use quantum entanglement phenomenon to transfer time information instantly to synchronize time between two places separated by large distance? I have not talked about these things. The answer is no. The answer is no. But if I start talking about quantum entanglement, I have to say more things about the current state of physics. So I will not talk about quantum entanglement itself, but I am saying we cannot send instantly synchronize anything. The only way to synchronize is to send a standard signal. The second question is, can you explain any inertial force as a consequence of gravitational interaction? So you've already forgotten my last lecture, or you did attend that, but you forgot it, in which I explained, I talked about inertial forces as a consequence of gravitational interaction. And if you go back, read the reference I showed you in the last slide, my paper, it has a complete explanation of inertial forces in terms of the gravitational interaction with the matter in the universe. There is a question from Neil Vadodaria. If the principle of invariance of time is not valid, why do GPS still account for corrections due to gravitational potential? I don't know what you mean by invariance of time. Probably you meant invariance of the velocity of light. Why do GPS still account for corrections due to gravitational potential? They are completely independent. Whether the velocity of light is invariant or not, gravitational time dilation will happen. A larger potential will slow down a clock more than a smaller potential. So that they are two completely different aspects of relativity. So even in a theory of relativity with an absolute frame, the same kind of gravitational time dilation will happen, and GPS have to correct for gravitational time dilation. Now, there's a question from Sherlock. Has the existence of gravitational potential has been proved experimentally? Now, I don't know what is exactly meant by this question, but if you take it at face value, it is a difficult question because let me say it also link it to the last talk. See, the only thing which is sensible to us, which is tangible to our senses, is matter and their movement. So the matter and their motion, charges and currents, are the only thing which are tangible to sensory experience. rest of the things like field, potential, all that is notions which we create and mathematically represent in our theories. We cannot see a potential directly. We cannot see a field directly. Nobody has seen a magnetic field. What people have seen is matter, iron filings distributed in a particular way in the presence of another material magnet. So therefore, when you say, ask whether the existence of a gravitational potential has been proved experimentally, if you are asking for whether somebody has seen a potential, not without using matter. In fact, even notions like space and time, they're all completely unobservable concepts. We can only see clocks, we can only see distance between material points and so on. So they have been proved experimentally, potentials have been proved experimentally in the sense, if we assume such a thing, there are some consequences which we can see using matter. In that sense, there is some connection between experimental observations and the concepts of gravitational potential and the field and so on. That's how I would answer in a short time. Next question by Vaishali. How will we synchronize individual nodes on future space-based gravitational wave detectors such as LISA? Same difficulties, as I said, the same difficulties for synchronizing clocks over 1 meter of distance will of course come in larger difficulty when you want to synchronize clocks across satellites which are 1 million kilometers away and so on. But the only practical way of linking time in clocks which are separated by distances is to send a signal. And it's an assumption, it's a convention that a synchronization has been done because it depends on the assumption on the propagation of light. But the difference, the gap in synchronization is a constant factor. So most applications, it may not show up. But if you notice the GPS, it's a one-way application. You send a signal from the GPS satellite to Earth, and that we detect. We don't send a signal from the mobile phone back to the satellite for verification. So it is in this one-way applications where the assumption, the wrong assumption shows up. There, these effects of Galilean velocity of light, the fact that the real relative velocity of light is not a invariant constant shows up, and that we have already saw proof because GPS has to use a formula which follows from the Galilean velocity of light. So that completes the answers to the questions. So I hope the audience have enough to think about and verify for themselves whatever I said in this lecture is factual. This is a fact. And you can draw your own conclusions. Thank you.